Okay, section 4 is over cell EMF under standard conditions, and we're going to look at the first thing dealing with electron flow. So we talked about earlier that electrons flow from your anode to your cathode. The reason they flow from your anode to your cathode is due to a potential energy difference. The energy is higher in your anode, which means that they're going to spontaneously then flow to a more positive potential difference. And so that potential difference is that potential energy difference. A lot of times this is called potential difference. Okay, the potential energy divided by your charge is equal to that potential difference. And it's between two electrodes. Okay, these are measured in volts, because a volt is 1 joule per coulomb. Coulomb is C, and that is a charge unit. Okay, so potential difference is the energy per charge. We call it potential difference. Slightly different, but very similar. One's per charge, and one is just more of a general, just the energy that something has. Okay, the potential difference is the driving force behind the reactions, pushing the electrons through the current, through the circuit, and we call that EMF, or electromotive force. Now it's called electromotive force because it's the electrons that are motive or moving, and that's the force that gets them to kind of move, that pushes them to move. That difference is the force pushing an electron to move from one spot to the other. If there wasn't any difference to push the electrons from one spot to the other, they wouldn't move. Okay, the E for a cell, okay, and oftentimes you'll actually see that CELL is kind of like a subscript. That is the EMF for a cell. It's usually in volts, and it's also called cell voltage. Okay, if your cell potential is positive, that means it's going to be spontaneous. So any positive cell potential is going to be a spontaneous reaction, something that is just going to occur. And again, remember that the cells there, we're talking about one direction, whether you're gaining electrons or losing electrons, either the reduction or the oxidation. Okay, standard reduction half cell potentials. This is going to be dealing with the backside of your periodic table that we have looked at with the upside down activity series. Okay, the EMF for a cell depends on the reactants at your anode, at your cathode, and the concentrations of them and your temperature. Okay, standard conditions again are those 25 degrees Celsius, the 1 atmosphere, things like that. Okay, a standard EMF or a standard cell potential. Again, we're dealing with the knots, the things with the little zeros up in the upper corner. Okay, there are too many possible combinations for an anode and a cathode. There'd be way too many E cells. So individual anodes and cathodes are found instead. Instead of having this reaction between when I use a zinc anode and a copper cathode or whatever, instead of using those overall cells, we do individual ones where we look at just the anode or just the cathode and not the actual combination. Okay, the cell potential is the difference between the electrode potentials, or between the two electrode potentials. A standard reduction potential, or an E with a knot with a RED underneath, and I'll draw it here in a second, is used to find your E cell. We can find a standard reduction potential by taking our cathode reduction potential minus our anode reduction potential, and we can figure out the cell overall. And if our E naught for our cell is greater than 0, positive, we're going to be spontaneous. So if you're going to find the overall reduction potential for a cell, the anode and the cathode, we take the cathode minus the anode, and we use the reduction potentials for each. Even though one is reduced and one is oxidized, we use the reduction potentials because we always use them in the form of something being reduced. And again, like I said a second ago, if your E naught for your cell is greater than 0, we're looking at something that is spontaneous. Okay, it's not possible to measure every half cell directly, so every cell has 2 half reactions. We use a reference, which is called an SHE, that is a standard hydrogen electrode. That is what we call a 0 voltage, because it's kind of like you're picking where you're going to start from. Okay, so we picked hydrogen as kind of the 0 point, the starting point, and everything else is based off of that. Appendix E has all of the half cell potentials, okay, and these don't change with a coefficient at all, okay, because if my joules go up, my charge goes up. So they work together. Remember, a volt is a joule per coulomb. Well, if I have more of the stuff, I have more charge, I also have more of my energy. So they go hand in hand together. And your reduction potentials are also found in the back of your periodic table. Okay, so if we look at the example here that you have at the bottom of the page and that I have right here, we have our cell, and they tell me that my voltage for the entire cell is 0.76. So the overall E naught for my cell is 0.76 volts. So 0.76 volts is going to be equal to my cathode minus my anode. So if I wanted to figure out exactly what the voltage for my zinc anode would be, I know that my hydrogen is 0, so we're going to take that as our kind of starting point. This is going to be 0, so I'm going to have 0 minus x is going to be equal to 0.76. Solve for x, and I'm going to get negative 0.76. And if you look on the list, zinc is negative 0.76. So they picked hydrogen as the 0 point and then read the voltages for a bunch of different cells and figured out what the other part of that would be. Okay, so if I look at my next problem here, it says for the zinc copper voltaic cell shown in figure 25, we have the reaction below. Given that standard reduction potentials for zinc is negative 0.76, I'm going to figure out the reduction potential for copper 2 plus to copper, and then give me my overall cell. So this really should not say RED, this should say cell. Okay, so my cell is the 1.10 volts is going to be equal to my cathode minus my anode. And I want to look at the copper, so you got to figure out which one is the cathode, which one is the anode. Copper goes from a 2 plus to a 0. Since it goes from a 2 plus to a 0, that means it has to be my reduction. It lost, or it gained electrons, became less positive and more negative. So that means that this has to be my cathode. So this is my copper that I'm looking for that I don't know, minus my anode, which is going to be minus negative 0.76. I solve for the copper, and I should get a reduction potential of 0.34 volts. And if we look on our chart, that should match what you have over there. Go ahead and try the next one. Okay, in this next one, you had the cathode and the anode because you're using the standard reduction potentials listed on the back of your periodic table or in your notes here. I have my cathode minus my anode. I got to figure out which one is which. I have my I minus is being oxidized, which means that that is going to be my anode. And I have my chromium here that is reduced, which means that it's going to be my cathode. So I looked that up, and I should find that this one is the 1.33. The I minus should be the 0.54. We subtract, and we get 0.79 volts. Okay, now it's all about what kind of drives your reaction. The standard reduction potential is the driving force for the reaction to occur. The more positive the reduction potential, the greater the driving force for the reaction. And your cathode should always be more positive than your anode. So on the chart here on the right, we have the cathode and the anode, and then the difference between the two is the cell. The more positive one is my cathode, the more negative one or the less positive one is going to be my anode. And it kind of gets my reaction to kind of actually go. So, and again, this is only comparing something to the standard hydrogen electrode. You can put whatever you want as the electrode to be your kind of 0 point, but most of the rest of the world uses hydrogen, so that's what we're going to use as well. So a voltaic cell is based on the following two standard half reactions. Use the data in E. Determine the half reactions that occur at the cathode and the one that occurs at the anode, and then our standard reduction potential for the cell. So I gotta figure out which one is my anode, which one is my cathode. Okay, if I look on my chart, it'll tell me that my E naught for my reduction for cadmium is negative 0.403. The E naught for my reduction from tin is negative 0.136. So that means the more positive one, which is this tin one right here, that is my cathode. The more negative one is the cadmium, that is my anode. So the cell is cathode minus anode. So negative 0.136 minus a negative 0.403, and I'm going to get 0.267 volts. The last thing we're going to look at here is the strengths of our oxidizing and reducing agents. It has to do with the E naught, okay, and deals with this chart. The more positive the E reduction value, the greater the tendency for the reactant to be reduced. Okay, that means that it is a stronger oxidizing agent. Okay, the more positive value is increasing strength of an oxidizing agent, which means it is actually very easily reduced. Okay, F minus has the largest E reduction, so it is the most easily reduced. I get the most volts out of that, so it is the strongest oxidizing agent. Lithium has a very hard time here at the bottom reducing. It would actually rather oxidize, which means that since it's more easily oxidized, it is a very strong reducing agent in the terms of lithium, like the solid. Okay, a strong oxidizing agent for a reactant means I have a weak reducing agent for my product. And as your E naught becomes more positive, it becomes stronger and stronger and stronger of an oxidizing agent because it is most easily reduced. I get the most volts out of that being reduced. Okay, the last example here. We're going to use 20.1. We're going to rank the following ions in order of increasing strength as oxidizing agents, which means that they are most easily reduced. So they're going to be the more positive E reduction values. So I look. Okay, NO3 minus has a positive 0.96. Silver has a positive 0.80, and chromate here, or dichromate, has a positive 1.33, which means we should go as the weakest one being silver, and then nitrate, and then dichromate.